Alrighty, here's my presentation for Physics 2211 Lab 1. Alrighty, so for an introduction here, this lab pretty much explored the motion and acceleration of an object, and with that comes Newton's first and second laws. So first law being an object in motion will remain in motion, and an object at rest will remain at rest unless they're acted upon by an outside force. So this outside force is going to have to cause a net force on the object. So meaning the forces do not cancel out, and this is what causes an acceleration. And along with that, the second law shows that the acceleration of an object is dependent on the mass and that net force that I was saying. So that's the F equals ma equation. With that, the lab also basically was just comparing the computational experiment to a physical one. So one that we used via a Glowscript, which is just basic Python, and then a physical lab that I completed myself. So the main two formulas that we needed for this experiment and lab was the velocity update formula and the position update formula, which are these two down here. So VF equals force times time divided by mass plus the initial velocity. And then the position one is the final position equals the initial position plus average velocity times delta T. So with this, here's the purpose of the lab. So it was, like I said, a computational model of an experiment to that was physically performed and tracked using a motion tracker. And along with this, to learn more about those first and second laws, like I said. So here's a diagram just to show how this is, while this object has net forces on it, the net force is equal to 0. So I guess there's technically not any net force. There's the normal force and the gravitational force, they cancel out, and thus there's no acceleration. So here's a physical experiment. I tracked it via this tracker app, and you can see basically each one of these is a little time frame in the video, and this gets tracked over time down here. So what I did was copy and paste this into a spreadsheet, and then that's what I converted to my graph later. So the initial physical conditions being this track right here had very little friction, and then I pushed it with a constant velocity. So while it was moving across the screen, it has the same velocity the whole time. That is what we compared to this computational model. So this we were just given starter code, and then basically all I did was edit it to be pertain to this experiment at least. So I took the average velocity of the cart from the tracker app basically, and then I changed it into this. So basically what that does is in the experiment online, it's going to start with this velocity. And then with that, I also changed the delta T just so I would have a little bit less data points, just because if I didn't, there would be 177 data points. So I changed that to 0.03. So every 0.03 seconds it tracked it. And then also I changed the while loop to be while T is less than 1.77, just because that's how long in this one, that's how long the cart went across. So I wanted to compare them equally. And then I changed the net force values to be zeros in all of them, because we want, in this experiment, we're comparing something that does not have a net force. It has a constant velocity, and that's why. And then the last thing, I changed the update velocity formula and the position velocity formula, which basically just aligns to those ones that I outlined earlier. So you can just see how basically ball velocity is the same as final velocity, ball velocity plus F net divided by ball m, F net T, blah, 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 and then delta T is right here. So it basically just converts over pretty simply, and this is just in the terms of the computer. So this is the comparison. So this is what the online one looked like, and this is what the two look like next to each other. So mine were pretty fairly similar. The only difference being this green one was the experimental, so it was a little bit more off. And then, so what does this result in? So we had a few possible sources of error, meaning friction, accidental net force, and tracker errors. And the what ifs, what if the axes were changed? So basically, if the axes were changed, the only difference would be the graph and the magnitude would be negative versus positive. So it's going to have the same magnitude, just in a different direction. And what does this mean? This means there's no exact way to measure and visualize all the pushes and pulls that act on the object, but we can know the net force is 0 since there is no acceleration. So there must be an equal and opposite force in either direction. And that's it.